Hi, everybody. How are you doing? Our plan for today is we gotta say three things on the agenda. So I want to finish. Excuse the 5-2 notes that we started last time because we're kind of in the middle of that. Questions from set 3, related rates, and then homework questions, time permitting at the end. Sound good? I did hand out set 4 just so I didn't forget it. I said it here. I saw Eva earlier today. I thought she would still be here.
She's empty. And she's closed.
So, Kylie, if you want to grab 4 of them and send them back, that'd be good. Excellente. Everybody cool with the plan?
Yes.
All right. So to just kind of rehash what we have done so far. So we started off this semester, we talked about this antiderivative process, just going backwards from our derivative shortcut in reverse, right? And then we said, okay, well, in some way this has to kind of be related to the area under the curve, because if I take a velocity, multiply it by time, I get a distance, which is kind of like position, and that's the antiderivative of velocity. So like some relationship has to be going on there. Let's try to explore that. In section 5.1 then, we looked at ways to approximate the area under the curve using these rectangles. That's called a Riemann sum. And we saw that, okay, if we take infinitely many rectangles then, that'll give us exactly the area under the curve. And in 5.2 now, we've taken that infinitely many rectangles calculation, given that a name, we call that the integral. And we're kind of exploring like what an integral can do or can't do, and we're kind of in the process of like, how do I do that computation? Everybody cool? So that's kind of where we're in the midst of. And in 5.3, we're going to kind of tie all this stuff together into a bow so that it like all fits together nice and neat. Okay? All right. We're not going to do part B. But I do want to do part A here for this example. It says set up an expression for the integral from 1 to 3 of e to the x dx as a limit of sums. Just too thick. Dial this down for me. It's going. Hi, Ava.
Hi, Dr. Cooler.
How are you?
Good. How are you?
Good.
That was bad. What?
Okay.
Beyonce and Jay-Z.
So we know this, right? This is the formula for an integral using a right Riemann sum. And we know that xi, well, let's do delta. Delta x is b minus a over n. And xi is a plus I delta x. Right? So that's like the formula that we're going to use. So for our particular problem, our value for A is 1. Our value for B is 3. And our f of x is e to the x. So far, so good. So we have the integral from 1 to 3, e to the x dx is equal to the limit as n goes to infinity of the sum I equals 1 to n. So our delta x is going to be 1 minus 3, or 3 minus 1 over n. Our xi is going to be 1 plus I times 2 over n. Oh, not 1, sorry. A is 0, right? Oh, no, A is 1. Okay. For n. Oops. And if I simplify that down, I just have like, I'm going to write it this way, just so it's a little cleaner. So we have then the sum of f of xi, right? So I'm going to take my xi and plug it into f. And then times delta x. Everybody okay? That's as far as I can go. The reason being is that if I go back and I look at all my summation formulas, they're all just for like polynomials of I, right? I have one for a constant, one for I, one for I squared, one for I cubed. I have anything for e to the I. Ooh. That's actually a pretty nasty summation formula. Everybody feel okay? So this type of translation, where we go from an integral to a limit of the sum, or if I go the reverse direction from the limit of the sum back to an integral, that would be a reasonable AP question for you. We wouldn't ask you to use the limits to actually evaluate like an integral. Too time consuming. I mean, you guys can do it, you're capable. But like as a test question, either for me or for the AP, it's too time consuming for either of us to ask for what you're going to demonstrate. So like that, what we just did there, where you use the formulas to do the translation from one form to the other, that's valid. That thing that we did last time that took like 25 minutes, inappropriate. Doable, you guys can do that. But like, I would not ask you to do that. They will not ask you to do that. Because it takes too much time. So far, so good? Okay, let's keep on kind of motoring through. So here it's asking us to evaluate these integrals by, instead of thinking about it as a limit, to use the area under the curve. So when you see the function square root 1 minus x squared, what is the picture of that in your head? Yeah, second hour didn't have an answer for me either. So let me ask you, let's do it together. Let me ask you this then. What's that? What's that? Or a circle. Yeah. So if I want to write this graph of a circle as a function of y, we can subtract the x squared over, and then we square root both sides. So we'd have something like that. It's also the graph of a circle, right? If I lose that piece of it, what part, how would I lose in my graph of a circle? The bottom half of it, excellent. Yes. Everybody feel good there? So I'll ask you again. Square root of 1 minus x squared is, what do you see? The top half of the circle where the radius is 1. Great. What's the center of that circle going to be? 0, 0. That's correct, Anthony. Can you tell us how you got that, or did you just guess? Perfect, yes. So because Anthony knows that, or remembers maybe, that the general graph of a circle with center h comma k, is this, right? Because there's nothing being subtracted from the x or added outside of the square root, we know that the center's just got to be 0, 0, right? So if I think about this graph then, that's the graph of that guy, right? So far, so good. Now remember that an integral is the same as the area under the curve. So our area is starting at 0 and going to 1. So we want just this little section, right? What is that? 1/4 of a circle. So to calculate this area, I can do 1/4 of pi r squared. Great. And what is r in our case? 1. Everybody okay there? And that area under the curve is going to be the same as the value of our integral. They mean the same thing, right? Does that feel okay? Let's look at the next one. x minus 1. What is that? What's the graph of that look like? Straight line, right. What else can you tell me about the straight line? Y-intercept at -1. And what else? The slope is 1, right? So we start at y-intercept -0, -1. And then we're going like 1 over and 1 up, right? Ooh, boy. So far, so good. So when I look at the area under the curve from 0 to 3, we're talking about those two areas, right? You can call this triangle 1 and triangle 2. Sound good to you? What do you notice about the area of triangle 1? It's smaller. Well, that's true, but what else? It's what? Negative. The area is negative. Why is it negative, Anthony?
Because it's the area of the
Well, it's because it's below the x-axis, right? The area of the curve that we're looking at is below the x-axis. So my area in general should be like T2 minus T1. So everybody feel okay there? So what shape are T1 and T2? What's the area of a triangle? 1/2 base times height. So what is the base and height for T1? 1 for each of them, right? That's 1 and 1, right? What's the base for T2? And what's the height for T2? 2. How do I know that? Because the function is x minus 1, so the y coordinate should be 3 minus 1, right? Nope, 0.5. Everybody okay there? This is a valid way of computing an integral. If the function is simple enough, you can do it geometrically. you think oftentimes the function you're going to be given is simple enough that you can do it geometrically? What other presentation would it be appropriate to want to resort to geometry? If you're given a graph without this, and just told this is the graph of f of x, compute this integral. If you're given a graph that these components can be broken down into geometric figures, that is what the AP is going to want you to do. That is a very common presentation where they're going to ask you to compute this integral graphically by using, geometry and breaking it into chunks, where you can calculate the area of this chunk using the area of a circle or a triangle or a square or whatever. Does everybody feel okay on that? Very common presentation. I'd be shocked if you don't see a multiple choice question where you have to do exactly that. Or multiple choice questions. This is the generalized formula for the midpoint, for a midpoint Riemann sum. Remember we gave the right-hand Riemann sum earlier? This is the midpoint Riemann sum. Notice that this is given as a approximation. Why is it an approximation instead of equal, a hard equal sign? What are we missing to make it a hard equal sign? How many rectangles do I need for it to be equal? Infinitely many. So what are we missing if I want this to be equal? The limit, right? If there was a limit there, then it's a hard equals. If I take the limit out, and I'm just doing this for finitely many n, it's approximation. Everybody's okay? So just kind of rehashing that. So delta x, still the same formula. But the way we're choosing our x's needs to be the midpoint, right? So these xi's are still the xi's from the right-hand rule. Everybody's okay with that? So they've gone and just kind of like have formula inside a formula inside a formula, which is, I love this when we do this, right? It's like, we just want the whole thing out with it all combined together. Because it's easier to format your book to do formula inside a formula inside a formula. That's really the answer to that. Okay. So this example says, use the midpoint rule with n equals 5 to approximate this integral. Okay. So I'm going to be using this formula up here. So the a is 1, the b is 2, the n is 5, and our f of x is 1 over x. So far so good? So that's going to be approximately, let's calculate our delta x. So that's 1/5. So far so good. To calculate these pieces, I need to have x1 bar, x2 bar, x3 bar, x4 bar, all the way up to x5 bar. To get those, though, I'm going to need x sub 0, x sub 1, x sub 2, x sub 3, all the way up to x sub 5. So let's kind of do that on the side here. So I'm going to calculate my x sub i's. And just kind of make like a little table here. So I have a, which is 1, plus 0, which is I, times 1/5, which is delta x. And I'm going to have a, which is 1, plus I, which is 1, times delta x, which is 1/5. And I just kind of continue doing this, and at this point, who can see the pattern on what these xi's are going to be? We need to plug the formula through for the last 3, right? Should be 8/5, 9/5, and then 10/5. So far so good? So here I'm going to have 1/2. If I is 1, then I minus 1 is 0, so I need x0, which is 1, and then xi, which is 6/5. So that's 11/5 times 1/2, so 11/10. Everybody okay? Oops, I should write write down what these things are. Okay. And if I want x2 bar, that's 1/2, x1, 6/5, plus x2, 7/5. That's 13/5 times 1/2 is 13/10. Anybody guess the pattern from here? What's x bar 3 going to be? 15/10, right? And then just kind of keep going up by 2/10. So notice that I didn't really have to like compute the whole thing out. I just kind of wanted to show you how I was using the formulas and then note the pattern and just kind of grind the rest of it out just using the pattern. That's all. Everybody's okay? Will the pattern always just be like plus some increment? Yes. Yes. The pattern will always just be plus something. Everybody's all right? Notice in each case the pattern is plus 1/5. Right, we added 2/10 for the x bars, and we added 1/5 for the xi's. Still the same, right? 2/5 and 2/10 and 1/5. All right. So now I'm going to do f of x bar 1, f of x bar 2, f of x bar 3, etc. So f is 1 over x. So if I do f of 11/10, it's going to be 1 over 11/10, or just 10 over 11. Oops. Got to flip it there, dum-dum. And I'm not about to make a common denominator there, but like you could grind that through in the calculator at that point. Mostly what I wanted to do this for was like an exercise and like showing you how these formulas all kind of hook together, right? And see the nesting of one formula into another that the textbook is doing, because it's, when you look at it at first, it's not super clear what they're doing. So I want to make sure I do an example. Does that feel okay? Again, what did we just find? That's an approximation. That's a Riemann sum using midpoints and 5 rectangles. Right? So just trying to connect some of the vocab together. Properties of definite integrals. These are things that you will want to have memorized. These are things that we'll use throughout the entirety of second semester. And often we'll have ignored it for like 3 weeks and then all of a sudden we'll have to pull one of these things out to use. It is what it is. But these are ones that you'll want to have memorized because they can make life much, much easier. So the first property says that I can switch the bounds of integration. So going from b to a, I can switch to go a to b. But in doing so, I negate my integral. I pick up a negative sign to do the switch. Okay there? Okay. If I integrate from a to a, that integral is 0. Why is that? Right, because you're talking about the area under a single point. What the width of a point is? 0, so the area under it has to be 0. We already kind of mentioned this earlier, right? But this is just formally writing it down. You're going to fight with me about this. The next one is if I take an integral of a constant, that's how I can compute it. Let's think about what this is really saying. What's the graph of like y equals a constant look like? Straight horizontal line, right? If I go from a to b, what's the area under that straight horizontal line look like? What shape is it? It's just a rectangle, right? What's the width of that rectangle? B minus a. What's the height of that rectangle? C. That's all we're saying, right? This is just really base times height. Because all you have is a rectangle. So are you okay there? What's property 2 saying? Yeah, you can kind of distribute that integral sign across an addition symbol, right? Could you do the same thing with differentiation? Can you distribute differentiation across addition? Yeah, definitely can. Why can you do it for both? Both integration and differentiation are just limits. Can you do the same distributing limit across an addition sign? So because it's a limit property, it trickles down to a differentiation property and an integration property. Does that feel okay? What are we saying in property 3? Yeah, as we can just take our constant and pull it out front of the integral, right? Can you do the same thing for differentiation? Yes. Why can you do it for both of them? Because you can do the same thing with a limit. It's still a limit property and it trickles down to integration differentiation. Okay? And then property 4 is just the same thing as property 3, it's just with subtraction. Who's surprised? Nobody should be, right? It's like if it worked for addition, I'd be really mad if it didn't work for subtraction. So we're going to use these properties to evaluate this integral. Okay. What property should I use first? Yeah, the distributive one, right? That allows me to rewrite this as the integral of from 0 to 1 of 4. And then I need my dx, and then my integral, or plus my integral from 0 to 1, 3x squared, and that gets a dx. The dx comes with the integral symbol when you distribute. Think about it as like the start of a parenthesis and the close of a parenthesis. Every integral symbol gets a dx at the end, or a d something at the end, depending on what variable you're using. Okay, so don't forget that. It's like the period at the end of the sentence. or the closing parenthesis for a parenthesis. Okay, what now? Pull the 3 out front. Yep, I like that. So Anthony says that 3 is a constant. I can take that out front. So really, like, there's a time symbol there. We don't have to write it, but ugh, you stupid thing. Now, could we do the same thing to the 4? It's a constant, right? If I pull it out front, what's left in there? Like a 1? Or just the dx is fine? You could do that. I wouldn't. You don't need to. What next? Property 1, right? Where I can just do C times B minus A. Very good so far? Now, what am I going to do with this integral of x squared? Well, I don't have a property that's going to knock that out for me. And I think what the textbook was intending was, if you looked at, the 5-1 notes, kind of the exemplar problem we did was looking at the area under the curve x squared from 0 to 1. So I think they planned on you using your answer from here to just substitute in. In an effort to like show you that limit thing again, I'm going to do that again. Is everybody okay? Because it feels like a good thing to do. So I'm going to have 4 plus 3 times the limit as n goes to infinity of the sum I equals 1 to n. So I have a is 0, b is 1, and f of x is equal to x squared, right? So I'm going to have my delta x is 1 minus 0 over n, or 1 over n. And my xi is a plus I delta x, or just I over n. So far, so good. So now I have f of xi. Remember, f of x is x squared, so I'm going to have I over n squared, and then times delta x. So far, so good. If I simplify this together, I get I squared times n over, or n cubed, right? Notice the summation depends only on I. That's my index variable for the summation. So I can pull that n cubed out of the summation. Is that okay? Because that's what I need. That is one of those 4 summation formulas that we gave you previously. So just to go show you what it is, it's n times n plus 1 times 2n plus 1 is what that's equal to. But let's just scroll up and just kind of show that to you where I'm getting that from. N times n plus 1 times 2n plus 1, over 6. Everybody's okay? So I'm going to go ahead and make that substitution. Keep on going, Kulik. There you are. Nope. There you are. So if I look at that limit, what am I taking the limit of? What type of function do I have there? Rational function, very good. Since my limit is going to infinity, what do I care about in the rational function? Well, I need to look at the degree of the numerator and denominator, which are both 3, right? The numerator is n times n plus 1 times 2n plus 1. That's 3 n's multiplying together, right? So that's an n cubed on top. I have an n cubed on bottom. If the degrees are equal, what do I look at? Leading coefficient over leading coefficient. What's the leading coefficient in the numerator? 2. Does everybody see it? So I have 1n times 1n times 2n. In the denominator, what's the leading coefficient? 6. So the answer is 5. Rather disappointed that all that work to just get that integral is equal to 1. Well, of course, sure. Pretty okay. Maybe, kind of. Another property. So we have the integral from a to c of f of x dx plus the integral from c to b of f of x dx equals the integral from a to b f of x dx. Yes, sir.
Will it ever work out to where that has a higher polynomial on top of the bottom?
Probably not. Not in the case of problems that I would assign for you guys to do. Would be the answer to that. So just like when we did the derivative calculation, how the h's all canceled out, the same kind of thing is going to happen here, where the n's kind of all cancel out. If not, you probably made a mistake. Good question. And you see the parallel of kind of how the algebra has to work out for this to work, right? Between derivatives and limits. Kind of doing this. The algebra is kind of the same, just a little different, but similar, parallel. So look at this property 5. What's really going on here? Let's think about this graphically, because it's super obvious why this would work. So let's say we have some curve here. Here's A, here's C, and here's B. So this first integral is that area, right? The second integral is that area, right? The third integral is that area. Everybody see why this has to be true, right? Basically, the thing that you want to look for is that the upper bound of one matches with the other lower bound of the other. You can hook them together into one integral. That's the idea. This is quite a useful theorem. This will come up a lot. I would expect a specific AP multiple choice question, essentially in the same form as this example right here, that basically tests, do you know your properties of integrals to where you can use these things, specifically that one that we just mentioned. So here we're told the integral from 0 to 10 of f of x dx is 17. Integral from 0 to 8 of f of x dx is 12. and we're looking for the integral from 8 to 10 of f of x dx. So the way I would do this, starting here, I'm going to look for the integral with 8 in it. That's this one, right? What do you notice about the 8, though? It's in the wrong bound, right? So we need to switch it. To switch the bound, what has to happen? We make it negative. Oops. So that's like negative 12, right? Or I should, just write it that way. Okay. The next piece, we look for the 10. We have that there, right? So that doesn't need to change. Oh my God, guys. Great googly moogly. There we go. You notice those are the same, right? If I add them together, I'm going to get this. Five is our answer. It would always just be subtract the two numbers. No, it depends on like the specifics, right? Sometimes they'll give you this piece and one of these, and you have to find like the one in the middle. Or sometimes they might have you hook 3 pieces together. It just kind of depends on the setup. But all we did was use our properties of integrals there. Essentially, just this property 5, and then flip the bound property negating is usually the only 2 that we do. Is that okay with everybody? Last set of properties. So it says that if f of x is always greater than or equal to 0, meaning that it's always above or on the x-axis, the integral has to be greater than or equal to 0. Because the area under the curve is always going to be positive if the function's always above the x-axis, right? If f is always taller than g, so f, g, the area under f will always be greater than the area under g. Okay, no dot, right? That seems pretty obvious. And then the last one says that if I have some bound for m, or some bound for f of x, where m is less than or equal to f of x and m is greater than or equal to f of x, so m's a constant, right? That's the bottom. F of x is in the middle. And then cap m's a constant. It's on top. The area under the constant is shaped like a rectangle. That's all this is, like base times height. Base times height. So the area under f of x has to be in between those two areas, right? Where one height is always smaller than the height of this rectangle, and this height is always bigger than any height in that rectangle. So there's upper and lower bound. Everybody feel good? Okay. It says use property 8 to estimate the integral from 0 to 1 of e to the negative x squared dx. So our first order of business would be coming up with a value for m, little m and big M. This would be the best way to do that. How would you go about finding a value that's always less than that function and always greater than or equal to that function? Yeah.
Plug in the 0 and 1.
Well, do you know that it's always increasing or decreasing? Probably not by looking at it, right? What else could you do? graph it. Yes, let's do that. Let's graph it and look at the picture, right? Then it'll be super obvious, like, okay, that's a number that's always less than or always greater than. Very good. Now, Anthony, it turns out that this one is, so there's that guy. This is the graph from 0 to 1. So it is always decreasing. But I don't know that you would have looked at that function and known instantly that that's what was going on there. I think that's asking a lot. Type in the calculator looking at the picture. So each tick mark here on the y-axis is 1 unit. I think. Let me go look at my window real quick. Yeah, 1 unit. So my lower bound I could use 0, seems reasonable. My upper bound I could use 1. It sounds fine to me. Everybody okay? Now keep in mind that what Anthony had said was, well, could I just have done plug in 0 and plug in 1 and use those as my bounds? Why didn't it spit out a value there? 1. There we go. Could I have done that? Yeah, that'll work. Because it is decreasing the whole time, that'll be fine. Again, like without graphing it, I don't know that I would have, or at least doing some derivatives and like making some analysis to find that it was decreasing the whole time. I don't know that I would have picked up on that without thinking harder than I really would want to about it, rather than just like, just graph it, take a look, and see what's going on. So I can say then we have 0 times 1 minus 0 less than or equal to our guy, less than or equal to, so somewhere between 0 and 1, or if you wanted to get a little tighter, it could be like 1 over e, is what we got when you plugged 1 in. That was the decimal. But that's it. And that was it for this lesson. Again, coming soon to a classroom near you, marrying these ideas of anti-differentiation and area under the curve calculation together, finding a connection between them, coming soon, i.e. Friday. Okay. All right. What I'd like to do next is to take questions from our related rates number 3. Sarah? Yeah, I have, up on the desk, I have all the sets here in a pile. Just set 3. Okay. That's set 4 on the top. Make sure you just read directions. All right. Let's start in the usual fashion where I'll read through the solutions for these problems and then we'll take questions. Sound good? Okay. For number 10, is what that number we're on, is negative 0.239 meters per second. And 11 is 20 over 3 meters per second. And then number 12 is 2.25 meters per second. And then 13 is 3/5 meter per minute. And then 14 is 75 miles per hour. Now these ones were, I would say, a very obvious step up in complexity or difficulty from set 1 or 2. Right? Did you guys have a harder time on these ones? They're considerably more challenging, I think. Are there ones that you'd like to do here as a group to kind of go through? Anthony? Number 11. Yeah. So I think my wording was part of the problem on this. So it says a spotlight is located on the ground 50 meters from the wall. The light rotates at a constant rate of 0.1 radian per second. How fast is the spot of light moving along the wall when the angle between the light beam and the ground is pi over 6? So this is kind of what's happening. And as time progresses, that's kind of what's going on. It's like moving up the wall. Okay? So if I add in the stuff, I'm going to call this side x and this side y. And I talks about the angle, so I'm going to add that in as theta. So if I look at my equation here, or I look for an equation, what equation is going to relate the sides of a triangle to the angle? Tangent in this case. How did you know it was tangent, not sine, cosine, or something else? Good. Opposite over adjacent. Everybody feel okay? Mr. Gulick, could I have done cotangent also? Yeah, but I don't know why you'd want to. But yes. Okay. So let's look at our parameters and see what's changing. Is x a variable or constant? Constant, right? What is x stuck at? Yeah, 50 meters. Is y variable or constant? Variable. Which means that we're going to need a dy dt at some point. And theta, is that variable or constant? So that means we're going to need a d theta dt at some point. Okay. Now let's look at what we're given. I don't know why I wrote 8 there. So we're told that the x value is, that constant is 50. The d theta dt is 0.1 radian per second. And we're asked how fast is the spot of light moving along the wall. So that's my dy dt when the angle between the beam and the ground is pi over 6. So that's kind of what we're trying to do. Does everybody feel okay in how I took the words and built it into a picture and then labeled my picture and took that and made that into an equation, how I looked at the equation, what was given, and filled in the parameters that I know and I don't know? This is the hardest part right here. Right? If you can get this far, the rest is usually pretty smooth sailing. I noticed that the only rate variable that I'm missing is the one I'm looking for, so no elimination of variable is necessary. So we're ready to just differentiate. And I'm going to fill in my constant for x. The derivative of tangent is, so I have secant squared. So the derivative with respect to time of tangent theta is secant squared theta d theta dt. And the derivative of y over 80 is going to be 1 over 80 dy dt. So far, so good. Okay. I'm looking to solve for dy dt, so let's start plugging in things we got. So we're told theta is pi over 6. Oops, and d theta dt we know is 0.1. So we just need to multiply both sides by 80 and then evaluate secant of pi over 6, right? Who remembers what secant of pi over 6 is from their unit circle? Square root of 3. So if you didn't remember, because most of us look with wide eyes there like, oh, I should know that, what could you do instead? Pi over 6 is what degree angle? 30 degrees, right? So this is a 30, 60, 90 triangle, right? What are the ratio of side lengths in a 30, 60, 90 degree triangle? Yeah. So secant is hypotenuse over adjacent. Or you could type it into your calculator, right? Now you type in secant in your calculator. You cosine pi over 6 and then take the reciprocal of your answer.
I think it'll be a arbitrary decimal.
Yeah. Yeah, if we wanted an exact answer, we had to do it this way, but like, on a problem like this, you probably have a calculator. But yes, sure. to get an exact answer. If this is multiple choice question, no calculator with an exact answer, yeah, you'd be stuck. Grinding this the rest of the way, which again wouldn't be terrible, right? Would be what? It would be 8 times 4, 32 over 3. Something like that. 0.1 times 80 is 8. And then I'd have 4 over 3. I think that's right. Did I turn this into 80 again? Gosh dang it, I did, didn't I? How come nobody's been yelling at me? Mr. Kulik, it's a 50, you bozo. I was like, that is not what I read though, guys. Okay. There you go. So 20 over 3 now. That is what I read. Ay. Anthony, you happy with what I did there? Was the hardest part the way it was written with the rotates and you thought spinning in a circle rather than like rotating up and down? I thought after I wrote it and you asked about it in particular, I'm like, just the rotates that was the confusing part. Because I didn't think it was going to be the calculus or the algebra. I figured it was like, that was confused at what the picture was going to look like. Yeah. So if you were to be asked a similar question on a test setting, I'd use better verbiage than rotate. Or imply somehow that it's like this kind of rotation rather than this kind of rotation. I was hoping like that you had the angle between the beam and the ground, you would have caught that like this is the rotating that we're talking about, but I think it was in the wrong order. Had I told you the angle between the beam and the ground was this, that's what you're looking for. When it rotates, then maybe you would have thought like okay, we're talking up and down. But I think the presentation on that question was maybe a little bit more. It's really can do better. It's hard. Are there others from this you guys want to talk about? Maybe just not really get to it, I don't know. I mean, a couple of you were absent, like total pass on. I didn't get too much. Did it go okay though? In general? So let me say this before we run out. I am looking to do an assessment on just this singular topic of related rates. Probably looking at sometime next week, tentatively like the end of next week. The assessment that I wrote is like 30 points total. So it's like a third of a standard test grade. Okay. The format, 5 multiple choice questions, 2 points each, 10 total points for multiple choice. 3 like questions like this where I don't give you, I just describe the situation, ask you to do all the stuff. Get to pick 2 to do. So I give you 3, you can pick 2 to do. Those are 10 points each, 30 total points. The multiple choice questions will mirror the stuff you saw in set 1 and 2. The big problems at the end, the 10 pointers will mirror the stuff you would have seen in sets 3 and 4. So I don't know that there's any brand new scenarios other than the scenario, that the problem types will be similar to what you've seen already in these sets. So if you're familiar with like, oh, okay, I remember this setup of like water draining from this thing, or like, like the person walking away from a street light and their shadow getting longer, like if you remember the setups, that'll help enormously. Because there's only really like so many setups you can do for problems like this. But I expect like you guys will do much better than what you're able to show on the semester exam on this topic after spending some time, like doing some real practice and like going through things and having a little bit more time to settle in with this. Then having it be your sole focus, I think will help enormously as well. I'd say calculator throughout, so you get a calculator the whole time. I'll give you any volume formula you need. Area formulas RMU. Deal. Area other than triangle, rectangle, circle, I don't know that you need to worry about. Like regular polygon, forget it. Trapezoid, forget it. Even though that's an easy formula. 1/2 base 1 plus base 2 times height. But everybody okay on that little assessment format? I don't want to call it a test because it's not really a test. But we'll cap it at like the time length 45 minutes or something to do 5 multiple choice and then the 2 regular problems like this. I think that should be pretty good. That gives you about 3 minutes per multiple choice question and then 15 minutes per regular question, which should be on the long end of what you would need to do stuff. Eva?
So the new grades beyond the assessment for like 4.9 through whatever we're doing or after this?
No, this is just a standalone because I didn't like what the performance on the semester exam was like for this and optimization. So we're going to do like another thing like this for optimization, maybe with the next chapter, where it just kind of like we work this in parallel. We have some little mini assessment in between, and then like we have our the normal stuff that we're doing, continuing on doing second semester stuff where it runs in the background. Sound good? I think that's pretty, right? Like, there's a better way of doing the review than just like stopping whole cloth and just doing this one thing for like 2 or 3 days and then testing on it. I like to spread it out a little bit, give you a chance to like, if I get busy, call back up or whatever. Sometimes it just takes time to absorb what's going on, like days may help. Are there homework questions, 4.9 or 5.1 that you guys want to ask about? We still have, 10 minutes of class. If there's other things, other related rates problems, or other homework questions that you want to ask about, I'm happy to do that. This is just me trying to provide more opportunity. Yeah.
There's some at the end of, I left my stuff at home, but there's some at the end of 4.9 that are like scoring problems.
Yeah.
So if we could do
The good ones, right? Okay. Sure. Let's do this. So I suspect one of them would have been this guy here. Did somebody in the second period ask about this also? So I'm just going to copy that in.
Yeah.
This sounds like a good one? Yeah. All right. So a car is traveling at 100 kilometers per hour. When the driver sees an accident 80 meters ahead, this must be why 80 was in my brain, because we did this second hour, and slams on the brakes. What constant deceleration is required to stop the car in time to avoid a pileup? Everybody okay with thinking about the situation? About what's happening? So, I know that this is like a acceleration velocity position problem, right? Okay. So I'm going to start describing the things that I've given in terms of like position, velocity, and acceleration. Try to like hammer this down so I can get into notation. I can do something with these numbers. So we're traveling at 100 kilometers per hour when we see the accident and slam on our brakes. So I'm going to call that v of time 0, right? Because that's the instant something starts to change is at time 0, we're going 100 miles an hour at that instant. Sound good? Now, v of some future time, I need it to be 0, right? I need to stop at some time later than 0 in the future so that I don't smash my car into the accident ahead. Are you okay with that? We're told that accident is 80 meters away. So my position at time 0, let's make that 0. And my position at that time t0, let's make that 80. I don't think it'll matter. I think it'll just be like, the algebra will be a little different. You get the same answer either way. But I suspect that'll make the algebra a little bit neater, doing it this way. If you remind me, I'll explain why I thought that in a minute, for when we get to it. Everybody's good with what I've done here as far as numbers? The last piece, and maybe the most important, says what constant deceleration. So I know that a of t is just a constant. That's what I'm going to be solving for, is that value for k. We're trying to figure out. Does that feel good so far? Okay, so now I'm going to anti-differentiate to take a back to velocity. So I've done that. I'm going to use v of 0 equals 100 to solve for C1. And I like that because the 0 cancels out the k there. So I got that guy. So far, so good?
Since 100 kilometers per hour and positions in meters.
Oh my God, yes. So annoying. Okay. I can do that, right? Let's do that. Sorry, thank you. Yes, 100%. I probably would have gone ahead and done it without the unit conversion. Our textbook loves to do this. It's such a jerk move to like, oh, let me throw a unit conversion in here on top of it. It's like, oh God, physics people. Am I right? All right, so we have this. We have a of t. Let's find s of t. So I'm just going to kind of keep anti-differentiating from here. And the reason I want to do that is because right now this really has like more variables than I can handle, right? So I'll anti-differentiate. So you can say that. I know s of 0 is 0. This is why I made s of 0 the 0 instead of the 80, because what that allows me to say is just that C2 is equal to 0. That cleans up the algebra a little bit for me. Not that it makes a big deal, but like any little bit I can get, I'll take. So I got this guy, right? Now, notice that the piece of starting information I haven't done anything with are these. I'm going to plug both of those now in and create a system of 2 equations that I can use to solve for, well, in really this case, I'll just worry about the k. I don't care about the t naught, how long it takes me to do that stop. So I have 0 equals k time, or k t naught plus 0.1. And then I have 80 equals k t naught squared over 2 plus 0.1 times t naught. that'll form like a system of two equations, because I have two equations with two unknowns. I'm going to solve this one for T naught. Oops, negative. And then plug it in here and just do like a substitution. And now I just need to solve for K. Which I don't think will be bad, right? What's this going to be? This is going to be 80 equals, I have 0.01 over K divided by 2 minus 0.01 over K. So that's going to be like 0.005 over K. Then I'll just multiply both sides by K. And that should be the constant of deceleration. And I'm relieved that I'm getting a negative value coming out of that. That's good. That makes me feel good about it. And the fact that it's like a pretty small meters per second probably makes sense to me. I don't know. I'm guessing. But it's going to work something like that is the idea. Maybe I screwed some little detail up in there somewhere trying to do this in a calculator, but Anthony caught the big one I was making where I screwed up the units. Does that feel okay though?
Yeah.
And again, notice that like I spent a good chunk of time like thinking about like what is the notation that I want to use going to look like? How am I going to write down the information that I'm given in the problem using that notation so I have like a way to represent this information and like tease out all the information that's given to me symbolically. Because if I can do this first steps, everything afterwards, the calculus steps are rather easy, right? The algebra at the end got kind of yucky. But the calculus steps were pretty straightforward. It was just translating the words into this given information. You know? And then once I have it in a form that's like symbolic, it's like, okay, now I feel good. I can rock and roll these symbols. The words are the scary part, right?
It's just like really like I didn't really think about like that kind of zero.
Yeah. So like all of these like physicsy problems, we're dealing with motion.
Yeah.
Think about time in there, like assign the starting time is 0 and some future time is, you know, some T naught or whatever. And that really helps. So if you take a calc-based physics class, this will be like kind of what things look like very frequently. So if your engineering is in your future,
Thank you, Doctor.
welcome to your everyday. You too.
I don't see that.
Okay. I'm just, you know, we're just talking, you know?
Yeah. Like my whole family's engineers, and I don't know how they like did all that.
You don't think you have it in you?
I know what they want. I think
It is, but like I don't know what you want.
Yeah.
What is your